We're excited to have Professor Rachel Hilliam with us. So, Professor Hilliam was Vice President of the Royal Statistical Society and the inaugural chair of the Alliance for Data Science Professionals. I believe that was only recently formed. She's currently Professor of Stats in the School of Mathematics and Statistics, where she's also head of school. So, without further ado, Professor Rachel Hilliam, take it away.
Thanks, Abraham. I'll just share my slides. Okay, so hopefully you can see that. If you can just give me a thumbs up, that's okay. That'd be great. Brilliant. Okay, thank you very much. So first of all, I want to say a huge thank you to all of the staff at Greenwich for all the work that they've put into organising what I think everybody will agree has been a brilliant event. Tony in particular does an enormous amount of work for this. And of course, the IMA and GCHQ for also their support and sponsorship. But actually, I want to say a huge thank you to all of you for your presentations. The ones that I've dropped into have been absolutely brilliant. So, and also the people that I talked to on Friday night, it's made me really excited about the future of our subject, actually, just hearing everything that you've got to say. So, thank you very much for all of you for your fantastic input and engagement over this weekend. It's been great. All right, so what I want to talk about, thinking about that future really, is some things that I've done over the course of my career as a mathematician. So, as Ibrahim says, I'm Professor of Statistics at the Open University, and I've kind of always thought of my career as a bit of a random walk, really. But in fact, when I've started to think about this more generally, and in recent times, what I've actually begun to discover is that actually, when you look back on your career, things that you think have been quite random have actually joined up in quite surprising ways sometimes. And one of the things that made me start to think about this was a podcast that I listened to about a year ago now from Steve Jobs. So Steve Jobs is in the co-founder of Apple. And what Steve did was he went to Reed University and Reed College, and there you were able to drop into lots of different classes on subjects that just interested you. So he actually went along to a class on calligraphy for no other reason than he just liked the beauty of the whole subject of writing and that sort of font and sort of beauty of that it gave him. So he didn't really think about that for years and years and years, and it was of no practical use to him whatsoever in terms of the work that he then went on to do until it came to designing that first Macintosh computer. And of course, in that, he kind of incorporated fonts and writing styles into that, which no other computer was doing at the time. So it was suddenly, something that he had found quite inspiring that he put into a completely different context. And he talked about the fact that it's only when you come to kind of the later stages of your career that you can actually join some of those dots together. So that's kind of what I want to talk about. I want to talk about some projects that I've done over the years, which have seemed particularly unconnected, but actually, when I look back on them now, maybe they're more connected than I might have thought about at the time. All right. So here's me. We're going to build up a kind of, like those postcards you get from your holidays, which is a bit of a wish you were here. So that's what I'm going to build up as we go through this talk. So starting over on that bottom left-hand side, that's where I went to university. So for people, some people may actually recognise that. That's the maths department as it is at the moment at Warwick. When I went there, it was in a completely different place, but I went there and did a maths degree. And even at that stage, when I was putting together this talk, I actually went back, which I've never done before. I went back and looked at the modules that I studied in my final 2 years at Warwick. In those days, there was only a 3-year maths degree. And certainly my last year, it really did, when I looked back on it now, look like a particularly random collection of modules that I happened to put together. So there was quite a lot there in terms of nonlinear systems. Considering that I actually have worked as a statistician for a very long time there's relatively little statistics in what I've studied there. So it does look a sort of fairly bizarre collection. And indeed, you might imagine from that I had absolutely no idea what it was when I was at the stage that many of you are now, what I actually wanted to do with this maths degree. So for no other reason than I thought I would be better off in terms of future employment opportunities, I decided that I would go and do an MSc in statistics, because I kind of decided that I'd never be out of a job if I was a statistician. And that was my sole reason for going to go down that particular path. And I also decided that doing an MSc in medical statistics might be more interesting than just doing straight stats. So I'd applied to various places. And what happened was as I was about to get on the bus to go and do my final year exam on catastrophe theory, De Montfort University phoned me up and said, "Oh, we've got this PhD. Would you be interested in doing it?" And at that particular moment, when I was about to go into that exam, quite frankly, anything seemed like a good idea. So I went off to De Montfort University to do a PhD in medical statistics without giving it very much thought whatsoever. So that's my kind of first bit of advice to you, really. Give things slightly more thought than what I did at the time. So that's the place that we're going to next, is De Montfort University. That isn't the maths department. Well, I was actually in the statistics department. There were two departments at that point. That's the chemistry building, but the department that I was in is now pulled down, so I can't give you a nice up-to-date picture of that. But it was a very horrible, actually, tower block that had a paternoster lift in there. If any of you have come across paternoster lifts, that you had to jump on and off as you want to get from one floor to another. So it's probably as well that I don't have a picture of that building to actually show you. So I went, as I say, over to De Montfort, and I did a PhD there, which was about statistical discrimination. So I was looking at particular disease types, and what my PhD was really about is if people couldn't give you a certain diagnosis, so those diagnoses might be open to misclassification, was there some way that we could actually incorporate that information and build statistical models? So that was essentially the nub of my PhD. What that was, however, was part of a much bigger project. So I was involved in this much wider project, which was looking at trying to develop a tutoring system. And it was developing a tutoring system for people who were radiologists, and they were describing brain scans for people that had got particular brain disorders. All right, so apologies for the grainy picture. This is the only sort of screenshot I've got from this from quite a long time ago now. So this is the idea of what the project was. So basically, we had a whole load of patients that went and had MRI scans to help them, help the neurologists at the time diagnose what their brain disease was. Now, for those of you that know anything about MRI scans, that whilst they don't look at here, there actually are high quality image scans, but they're also a very flexible imaging type of technique. So it depends very much on the sort of sequence type that you take as to whether you can actually, from a single picture, see the sort of abnormalities that you're looking for, because you take many, many what are called slices, so many, many pictures as you do these particular scans. So if you're just looking at one picture, you can have that sort of problem where you might not actually see what it is that you're trying to look for. Also, there was a problem that people sort of describe these things in many different ways. So what we were trying to do is to create a sort of unified description language in some ways to try and help people as they were training to be neuroradiologists to help use this sort of common set of language to be able to do this diagnosis. So this is what the tutoring system looked like. Whereas on this left-hand side, you've got the particular person that you're trying to diagnose, and they've got a particular disorder. Down here, you get asked on the bottom left-hand side, there's a list of prompts for you to kind of click on what you think this scan looks like as you go through various questions. And where I came in is on the right-hand side of this. So on the right-hand side, what we've essentially got is a image space. So it's a sort of pseudo probability space to a certain extent down there. So this white dot is the image that people are trying to describe. And what they can do is they can bring up other patients. So people with other each of these spaces are the same disease, so they can bring up somebody else with the same disease, look at all of the different scans for that particular person, and use that to help them come to a diagnosis for the person that they're interested in. So how far away each of these other points are, as you can imagine, has got some kind of statistical modelling behind these. And that was essentially where I came into this. Now, the problem with this was that whilst there were a lot, so there was something like 1,000 different patients that we had data on in order to be able to build this up. But from those patients, many of them had a working diagnosis as opposed to a true diagnosis. So it was a case of how we could use all of that information when some of those diagnoses weren't actually certain, so weren't actually the disease potentially that these people might have got. So that's what a lot of my work was kind of around, was how we might do something to be able to incorporate this working diagnosis. So I'm going to give you an idea with a sort of cut down, sort of simplistic model of this, which is kind of where I started with this actually. So for those of you that have done various statistical modeling courses, we're going to take a situation where a patient might have two different diseases. So a patient can either have a diagnosis of multiple sclerosis, or there can be a vascular patient. And the reason for starting with these two diseases is actually it is very difficult. It is very easy to confuse these two when you're looking at the brain scans for people with this particular disease. And one of the reasons for that is multiple sclerosis. This is a disease where your brain is coated with a myelin sheath. And actually what happens is you get degeneration of that myelin sheath, but it happens over periods of time. So it can sort of flare up and die down. So depending on the time when you do your scan, it can look like it's there, or it can look like, in fact, it's something else. And the something else that it can look like is actually very similar to a patient that's got a vascular disease. So for an example of a vascular disease, these are things like, well, the brain is obviously fed by your blood supply in terms of oxygen and various nutrients and so on. And if you have an insufficient supply of blood to your brain, that's called kind of ischemia there. And one possible consequence of that is brain swelling. There's also many of you will be aware with sort of flights and things, you can have clots that travel all the way to your brain. So you can end up with, in fact, an infarct in your brain where a part of it dies. So each of these things can be quite often confused with a diagnosis of multiple sclerosis. So we're going to assume that any patient that we're looking at is either a multiple sclerosis patient or a vascular patient. And in an ideal world, we could do some sort of logistical regression model there. So we've got a probability that a patient with a symptom profile L is going to be a patient that's got multiple sclerosis. And we can just follow that through quite easily with our logistic regression. So they've got some sort of explanatory variables, and we can have some sort of regression parameters for that as well. Okay, so that's all fairly straightforward. But as I say, what I had was a case where actually not all of those people, we knew that that was a true diagnosis for them. So we got all of the clinicians as they were given these diagnoses to sort of tell us how certain they were that the diagnosis they were giving us was actually correct or not. So what we could do is come up with something like a measurement, let's call it alpha, to say that our patients have been misclassified. So there's two different ways that that diagnosis could be misclassified, given that we're only assuming they've got these two possible diseases. One is that they've got this probable diagnosis, which is a vascular disease, where in fact they really do have multiple sclerosis. And the other way around is that they've got a probable diagnosis of multiple sclerosis, when in fact they really do have a vascular disease. And like all of these things, and this is going to be a bit of a theme through the talk, there's various assumptions that we make in there. And one of those assumptions is, in fact, that this has got a common misclassification, let's say, between those two different diseases. So it doesn't matter if you've misclassified your multiple sclerosis patient or your vascular patient, we're going to assume that that misclassification rate is the same. And actually, when you look at the data, that's not an unreasonable assumption to make. But I think this is the sort of thing that we need to bear in mind a lot when we are working as mathematicians and statisticians, is about really being able to identify very clearly, not just to ourselves, but to other people, what those assumptions are and where we might need to relax those assumptions, and also what limitations having put those assumptions in place have got in terms of what we're telling other people. So that's a kind of theme that's going to run through this. So I'm not going to talk too much more about this, but you can imagine then we've got a situation then where some people have got what we're going to call a true diagnosis, because the clinicians are pretty confident that their diagnosis is correct. And then we've got another set of patients, which is the right-hand side of that table, which has got this probable diagnosis. And we can essentially set up what's the probability, given this misclassification, of them having a true disease, which is multiple sclerosis or vascular disease. And then it's reasonably easy to state what your likelihood for any particular patient is in that particular scenario down there. Okay. So in order to then estimate what each of these things are going to be, we can set this up to a certain extent as if it's a missing data type of problem. So there are lots of techniques out there. Some of you will have come across some of them. One in particular is this technique called the expectation maximization likelihood, where essentially you can look at your model, you can pick out the bits that you actually do know, you treat the rest of those parameters as missing data, and then you maximize by estimating over the bits that you know, you then maximize so you can actually identify those missing data parts of that. So it gets kind of quite messy in places, so I'm not going to talk about that very much more, but essentially you can do lots of different optimization techniques and also Bayesian techniques as well. But the point that I really want to make about this is that this was my first foray into something where I had really quite complex data. So you can imagine this image data is not something that you've just got nice and neatly on a spreadsheet. There's lots of decisions that you've got to make about what data you're using and in what ways you're actually capturing that data as well. So at each stage of going through this, in order to build up that model and that nice kind of picture on the right hand side where I've got patients quite close to each other, there are lots and lots of decisions that I had to make about the data there. And I had to make those in consultation really with the experts, because I don't know about brain disorders. So there is an awful lot there of conversations that need to take place, and making sure that you're asking the right question. And I think there again, that's something else to hang on to as we go through this, that making sure that you're asking the right questions. All right. So I was at De Montfort for about 5.5 years. In fact, I was there for more or less exactly 5.5 years. During my PhD, I also ended up getting a job as a full-time lecturer there. And I could have stayed there, but in fact, I decided that I wanted to go off and do something else. I've actually got a really quite a heavy teaching load as well. So I went to the next place that we're going to talk about. So the top picture there, top middle picture, that place is Birmingham University. And I went to Birmingham University and essentially gave up my completely secure permanent lectureship to go and do what was really a 3-year postdoc at Birmingham. So it was an EPSRC fellowship, but it was a really interesting project for me, which is one of the reasons that I went to do this. So this was a project where I teamed up with engineers from Bologna University, and these engineers were interested in communication systems. So they were particularly interested in using dynamical systems, so chaotic dynamical systems, in order to embed communication messages within these chaotic systems. So where I came into this project again, I was sort of intrigued by this project as we were looking at some of the statistical aspects that these models might have. So to give you a bit of a sort of thought as to why any of this might be useful at all. So if you have higher dimensional chaotic systems, so many of you will be familiar with chaotic systems in one dimension, so things like your logistic map. Well, you can have lots of these in multiple dimensions. I'm going to reduce it down to just 2 dimensions, so looking at bivariate maps. But what's in fact quite amazing about these is that you can actually synchronize, if you've got 2 of these 2-dimensional chaotic systems working alongside each other, you can force one system to synchronize with the other just by putting part of one system through that. So you can kind of drive what's happening in one chaotic system by a component from another chaotic system. So if you think about it, this is actually really useful in terms of communication terms, because it means you can embed essentially your binary code in your transmitting system. And what you might need then is exactly to know what those starting points are in old money in your receiving system. But in fact, if it's the case that you can force that receiving system to synchronize with your transmitting system, then in fact you might not need what those initial conditions are. And in fact, that is the case. So there's a certain amount of security then that is established by not having to have both your transmitting and receiving ends knowing all of that information around those initial conditions. So this is something that the engineers were really excited about, and something that I started to work on with them. So I'm going to give you, this is the most mathsy bit of the talk. I'm going to give you some of the kind of maths and some of the statistical ideas behind what I was doing whilst I was at Birmingham. So change of gear then. So we're going to think about a bivariate map. So this is a map over 2 dimensions, X and Y, and our map we're going to say is Tor. All right. So when I'm talking about a system here, I'm talking about where X and Y move to as each iteration of that map goes along. And we're going to assume that all of those iterations, all of those points are enclosed within a particular region A. And what I'm going to do is I'm going to explain some of this using an example of the bivariate-Arnold cat map. So the reason for doing this is that it's actually really quite tractable, all of the mathematics behind this. It sort of looks quite messy, but in fact, there's no particularly difficult mathematics in there. So everything drops out reasonably, well, certainly within a closed form. I wouldn't say easily, but certainly within a closed form there. So it means that you can have quite nice results coming through from that. So here's our Arnold cat map. So basically a point x is going to be derived by x plus y in the previous iteration, and the point y by x plus 2y all over mod 1. So in fact, this is what our map looks like. I'm just going to check you can't see that. Okay, so this is what our map looks like, where we've got this square, our unit square, and we can split this square up into 4 different regions, and we can define those regions quite easily by the lines using that map. Okay, so essentially what that means is over those 4 regions, we could think of that map having 4 different forms. And that's just useful because it means we can do various things fairly straightforwardly in a mathematical way. Okay, so when we're thinking about a chaotic system, what we're thinking about is if we start with 2 points really quite close by, we're assuming that in a chaotic system, those are going to diverge relatively, well, maybe quickly, but certainly going to diverge over time. So what actually controls that diversion, if we're thinking in multiple dimensions rather than in 1 dimension, is actually something that's called our Lyapunov exponent matrix and the eigenvalues for that. So I'm just going to give you a brief sort of overview of what that is. So as I say, what we're going to do, we're going to think about 2 points that are close by, and we're going to run our map on those 2 points and see how far away those 2 points are after a time t. So our 2 points here are x, y, and x prime, y prime. Okay, and it turns out that, you know, fairly approximately, but yeah, pretty good approximation is if we took the Jacobian matrix and we looked at that Jacobian matrix at the previous time point and multiplied that by how far away these 2 points were at that previous time point. And that gives us a pretty good approximation for how far away the points are at the time point now that we're interested in. And if we take that iteration all the way back to our initial condition, well, basically we're just multiplying those Jacobian matrices together, aren't we? So what we end up with is this thing that's called our Lyapunov exponent matrix. Okay, so this is what we're interested in, and this is what actually drives whether this system is going to be divergent or not. So I'm just restating that equation at the top of this slide, just so that you can kind of have that in the back of your mind. But essentially, as t goes on, as our time period, as we work our way through that time period, we can have a look at how far away these 2 points are from each other. And as I say, that's going to be driven by this Jacobian matrix that we multiply up to get our Lyapunov matrix there. And we look at the eigenvalues of that particular Lyapunov matrix. So essentially, you don't need to follow this because we're going to just look at an example for this. But essentially, this lambda is derived from the largest eigenvalue of that particular matrix. All right, so that's all we need to remember, is that we're looking at the largest eigenvalue there. So we get divergent behavior if that eigenvalue, that lambda, is greater than 0. So, you know, that's fairly obvious from this equation here, isn't it? If this is greater than 0, it's going to mean that those 2 sequences diverge from each other. But what you need to keep in mind is that the direction of the divergence is going to be along the eigenvectors. It's not necessarily going to be along the x and y axes. So that's kind of quite important if we're wanting to think about the dynamics of these maps, particularly if we're wanting to know if we're embedding our binary message in a particular X or Y within that map. We might also want to know about whether there's divergence in that X or that Y direction as well. Well, it's not kind of that difficult to be able to work out that we could actually come up with some approximation for that divergence along those individual sequences as well. And I assume the slides will be available for people afterwards, that you can look at that in a bit more detail, but essentially the maths isn't all that difficult, and we come up with something that we've called marginal Lyapunov exponents there. And again, it's whether these are positive or not that drives whether we've got that divergence in any particular X and Y direction as well. Okay, so let's look at what this looks like for the cat map for a moment. As we said, we've only got one fixed point of that map, which is the origin, which is 0, 0. The Jacobian matrix is pretty easy to work out. You can do that just from looking really at the equation up there. So that's a constant matrix, and it's got rows 1, 1 and 1, 2. And therefore, our largest eigenvalue is going to be, 2.6 and a bit there. So we've definitely got divergent bivariate behavior for this Arnold cat map. Okay. So as I say, we can look at that in each direction as well, and it's relatively easy to again work out what happens in those univariate directions, and we end up with these marginal Lyapunov exponents. If we work through all of that, we again see that those are going to be log 3/2, both for the x and y direction as it happens for that. So we've got nice divergent behavior both in terms of bivariate dynamics and also in terms of each of those x and y directions as well. So that's great. That means that it's going to be nice and messy. If we use this for any sort of communication type of system, it's going to go all over the place, which is exactly what we want. So what I was interested then in is what happens then. What does that mean about the statistics? So you can think, can't you, that as you are looking at sort of realizations, if you like, of this map over time, what you in fact get is something like a time series, don't you? So you're starting off with an x1, x2, x3, x4, and so on, and you can build up time series. So if you've got a time series, then you can have a look at what the distribution is for that particular series. So that's what I wanted to do here, was have a look at what's called your invariant distribution. And in order to do that, one way to get a handle on this is to actually think about the sort of pre-image structure for those maps. So any map can have a unique pre-image structure, or it could be that you've got multiple pre-images there as well. Certainly that's the case for many of these sort of bivariate chaotic maps. But it so happens that the Arnold cat map's particularly nice, and it's just got one pre-image for each point that we're interested in. So again, that means that things are much easier to be able to work out, and we can in fact fairly simply note where each of those regions comes from by just working this through. What this means is that essentially each of those pre-image areas splits the regions that we're interested in into 4 subregions. So anything that we want to work out, we can basically look at lots of subregions and do the mathematics on those subregions. So you sort of get lots of bits of mathematics, but none of it is particularly difficult to put together. So it's something that all of you can kind of follow through if you wanted to look at the maths of this in your own spare time. So as I say, what we're interested in then is I'm going to set this up as a bivariate random variable. And what I'm saying is that this has an invariant distribution of the map if the inverse of that map is equal in distribution to our random variable itself. Or equally, we can do it the opposite way around and say that actually does the image have the same sort of distribution as well? Okay, and the way that we look at that is by looking at whether the probability is less than or equal to whatever it is that we're interested in, and whether that's equal to the pre-image structure having that same probability. And as I say, if you've got multiple pre-images, then it all becomes a little bit more complicated and you need something called the Perron-Frobenius operator in there. But that's definitely one not to do very quickly at the moment. But again, there's more details in some of the references that are in these slides if you're interested in that. So let's have a very brief look at what this means for your Arnold cat map. Well, as I say, it's kind of quite useful because it's statistical properties. We can obtain those explicitly because it's got this nice linear structure to where all of those different regions are. And amazingly, it turns out that actually there's loads of independence, which is sort of amazing when you think what you're actually doing in terms of, iterating this. And you've got this quite divergent structure, as I've explained in lots of different ways. So how do you prove this? We're only going to sort of look at one little example here. How do you prove this? Well, you consider whether the probability when you've applied your map to the random variable is going to be equal to xy. And if it is, that means that your invariant distribution is essentially uniform over that square. And you'd need to do that sort of calculation for each of those different regions. So all that means is that you get a kind of lots of inequalities down there, but you've got a little bit of a complication in that the form of any of those areas, it ends up being the integral of sort of 6 different regions that you need to look at. And as I say, we're going to skip over this because it's not all that interesting, but is just kind of time consuming to do. But for example, if you took the second of those, you do this integral over all of those different parts of it, and you find that is equal to xy. And you find the same is true for all of those different bits. So the point to take home is that you've got this nice invariant distribution, which is uniform over that square. So that's great. But what's kind of quite amazing about this is not only do you have independence from that point of view, but in addition, each of your sequences also has independence in there. So for instance, the x and the xt minus 1 are also independent. And the way that you'd show that is doing a similar sort of calculation and showing that each of those random variables, the probability when you get down to it is also equal to xy, which is indeed the case. What's even more surprising is that you can do the similar calculations and show that each of these other pairs, they're also independent. So in fact, what we end up with is that we've got this bivariate map which has got all of this divergent behavior in all sorts of different directions, but it's got a huge amount of independence in it, particularly when we look at those sort of individual sequences. So, of course, because it's got this dynamical structure, it can't produce independent pairs, but it can produce independence in those individual sequences. And it's this sort of thing that's kind of really useful from that point of view of understanding all of the, not just the dynamics, but the statistical behaviors of these maps when it comes to that application about whether it's going to be useful or not. So again, what I kind of learned from this is, whilst the maths was absolutely brilliant, I absolutely loved doing this project, and there's many more sort of maps that I looked at, which are far more interesting than this one. But again, it came back to those conversations with the engineers to kind of really get into their mind about what it was that was going to be useful for them in this sort of practical application, where I just sort of then went off and played with the maths and made lots of pretty pictures, really. So again, it's that having those conversations and being able to ask the right questions of the people that you're working with, particularly when you're working with people who are in different fields from you. All right, the last example that I'm going to talk about in detail is then when I left Birmingham. And I actually came out of academia for a few years, and that top right-hand picture is Derby Hospitals. So I went from Birmingham to Derby Hospitals, and I worked there as a medical statistician, and I worked there for 8 years. I think it must have been something like that. And basically there I was looking after all of the research and development that went on. So lots of clinical trials, also lots of not just clinical trials, but kind of evaluation of different techniques, also looking at various bits of patenting different medical devices as well. So it was a really interesting job, and I got to work with lots and lots of different projects down there, which I'm not going to tell you about in huge details, but I'll leave those up there because we'll run out of time. But the one that I do want to tell you about is this one. So this was a project that went on for quite a number of it. In fact, most of the time that I was at Derby, we were running this project. It was one of the first projects that I actually got involved with there. So here, what we were trying to do is come up with a measurement tool for assessing somebody's quality of life. And this is assessing their quality of life when they have lymphedema in a node, and not in a node, in a either leg or arm. It happens we came up with 2 slightly different variations on the tool. So I'm going to refer to this as LymphQOL. And what we wanted to do with this tool, we wanted it to do various things. So one of them was assess the impact that lymphedema had on individuals. So this can be quite a painful disease, but it also can have lots of different effects on people in terms of their, not just their physical symptoms, but also physical and social functions, as well as quite emotional effects. So there were various aspects that we wanted to measure with this particular quality of life tool, as well as something that you might think is obvious in terms of how their quality of life changes as a result of treatment. But we also wanted this tool to be a practical tool to help with treatment decisions, as well as kind of assessing whether it was effective, or both in terms of clinical effectiveness as well as cost effectiveness. So essentially what this tool is, it's a quite a comprehensive questionnaire, and it covers 4 different areas. So it covers the symptoms, the body appearance, the functions that the patients can still do, and the mood of those patients. And each of those 4 different areas, there's a whole load of questions for each of those, and each of the questions is scored between 1 and 4. Okay, and then those scores get aggregated together to give us a score for each of those 4 different dimensions of the questionnaire. So there again, as you might imagine, as people answer this, there's quite a lot of missing data in there. So there's things that you need to put into that questionnaire in terms of how you're going to cope with that missing data, and what you're going to do in terms of creating measurements. So again, that's a kind of slightly different talk, but something that you need to think about. So what I want to give you an idea of is, when you come up with a measurement tool like this, or even any questionnaire, I would argue that there's certain things that you really should think about in terms of what these tools are doing. Okay. So One thing that you need to think about in terms of when you're validating this tool, and it may seem fairly obvious, is the scale measuring what you're actually wanting it to measure? That seems reasonably obvious, but actually, when you start to think about the different aspects of that, it's more complicated than you might think, and I'm going to show you that in a moment. You also want to think about the reliability. So does the scale, can it be reproduced under different conditions, which is true for much of research that we do, but also the responsiveness, as in, when people have had a treatment or when there's some change that's taken place, is the scale sensitive enough to be able to record that? So as I say, this thing about does the scale measure what we want is more complex than you might think on first value. So one thing is something called the face validity there. So what we did to try and assess this was bizarrely give people a different questionnaire, which was really asking people in a short questionnaire about this measurement tool that they were completing. So it was a fairly short thing where it just had the following questions in there about, was it easy to complete? Was it too long? Were the questions clear? Did it include the important areas, and were the things that you thought were missed out? And we gave this to all patients, and we analysed that alongside this tool that they were also completing at the same time. So we got some idea from this about whether it was sort of doing its job. Alongside that, there's something called content validity. So in other words, you want to make sure that you're not kind of missing anything there. So we did interviews with about 22 different patients just to check that there wasn't anything as we went through these quite comprehensive interviews that this was missing. There's also something called criterion validity. So in other words, what you ideally want to do is to compare your mu measurement with a gold standard tool. Now, there wasn't any tool out there that did this, which was part of the reason that we were doing it in the first place. But what we did was we knew that there was a measurement tool out there which was looking at cancer treatment and quality of life more generally. So we gave that measurement tool to the first 50 patients in this study and kind of compared the relevant sections just to check that it wasn't doing anything different from what essentially the already validated tool was doing. And the last parts of this is you also want to check that, if you remember, I said there's 4 different domains that you're looking at. You want to ensure that there's consistency within those. So there isn't any question in there, for instance, that isn't really related to that domain. So you can do that by kind of splitting the questions in half. So and just checking that each of those halves are measuring, or each of those halves have the same sort of measurements that you might expect. So we did this by splitting it in half. So we took the first lot of questions and the second lot of questions, and also looked at odd and even questions and did, various bits of statistics on that. We also did a bit of test and retest in a subgroup of the patients there by giving them the questionnaire when they came for their initial assessment and then just before they had treatment, because nothing really should have changed in that time, just to check. And the last thing in that is also something called construct validity, where, is it really measuring what we think? Well, we got this kind of hypothesis that if your limb was very swollen, then it was likely that we're going to be suffering more pain and so on. So we did a check in terms of measuring people's limbs for this as well. Okay, so obviously we wanted to also see how the tool changed over time. So we did lots of follow-up of this after they'd had treatment. We gave them the questionnaire again at 1 week, 3 months, and 6 months. And again, you get missing data problems the more that you follow up those people there. So what I really wanted to say about this was actually, out of all the work that I've done, this one's probably had the most impact. So the NHS absolutely use this. This is their gold standard now for people that come with this condition, but it's also been translated into multiple different languages and people use it all over the place. But what I really want to pull out of this for this talk is the fact that there again, this was something I didn't know anything about validating a new tool at the time. But what I had learned from previous projects that I'd done was actually what we really needed to think about was trying to extract from the experts the sorts of things that could be measured. And not just the sorts of things that could be measured, but actually what we might be missing there. So the more and more that I do of different studies, the more and more that I think it becomes important to think about not just data that you're collecting, but data that you haven't collected and what that might mean in terms of implications. So for instance, if we'd had this measurement tool and hadn't applied it to anybody who, well, let's say we hadn't applied it to any females, then actually we're missing a whole chunk of the population there. So I think we need to be more aware in our lives of sort of data that's actually missing. So the last minute is that then I'll go to the Open University, and basically, as Ibrahim said at the beginning, I've done lots of different roles there, and I'm not really going to talk about any of those because we'll run out of time. So I'm going to skip through those and basically leave you with something about what I feel in terms of now when I look back and thinking, well, maybe my life wasn't such a random walk in terms of through these different career stages. But actually, I can now go back and join the dots. And the dots that I join together are partly about talking to lots of different people and really understanding the questions that I should be asking them. And alongside that, part of that questioning is, as I say, thinking about the data that hasn't been collected and actually what we should have thought about slightly more carefully. So I want to leave you with a reference to a book by David Hand, which is called Dark Data, where he talks about all of these different types of situations where you might have data that are missing because of a whole range of things that we've not actually talked about and discussed. So when I look back, I think actually maybe my career isn't such a random walk, and maybe it is that director graph, but it's only that because I can now think about it in terms of joining those dots together. And I will leave it there.
Thank you, Rachel. That was a wonderful talk and a wonderful way to end the conference. You brought up a lot of very important topics, and I always find it interesting, being at that age myself, looking back in one's career and seeing the interaction between randomness and serendipity and planning. So, Rachel, did you ever imagine when you were doing an undergraduate degree that you would have a career trajectory like that which you've had?
No, it's a short answer to that. Absolutely not. And I don't think actually at any point I sort of thought that that would be the next step in terms of what I'd do anyway. So I think that's my one bit of advice that I'd give to people in the audience now, that you kind of just grasp the opportunities as they come along and sort of don't worry too much about what the future is, because you never quite know where that path is going to go.
So I think we'll thank Rachel very much for that wonderful keynote talk. And thank you very much, Rachel.
Thank you.